Hi, I'm Hamuel, and I'm here with Jericho to show you an experiment about elasticity, specifically an experiment about Hooke's law. This video has chapters if you want to skip to any part of it. So, what is elasticity? Well, if you want, you could try to think of your own definition and you could compare it to ours. You could even pause this video if you need more time. If you don't want to do that, then it's fine, it's completely up to you. So, elasticity. It is the ability of an object to revert to its original shape and size after being deformed. Now let's talk about the restoring force. What is the restoring force? It is the force that acts opposite to the displacement of the body. Let us say you have a spring with a mass attached to its end, pulling it down. Then, the restoring force is a force pulling the spring up with the same magnitude as the weight of the mass. Hooke's law says that when a spring is stretched or compressed, there is a restoring force that is proportional to the displacement. The restoring force equals the negative of the spring constant, the quantity that measures the elasticity of the spring, usually represented by K, times the displacement of the spring, represented by X. Now, let's solve this sample problem. A 6.0 Newton load stretches a coil spring from 3.0 decimeters to 5.0 decimeters. What is the spring constant? You could pause this video if you want to try it yourself. So, let's see what we have. We have the weight, which is 6.0 newtons, the initial length, which is 3.0 times 10 to the negative first meter. We're using scientific notation, by the way, to keep track of the significant figures. Lastly, we have the final length, which is 5.0 times 10 to the negative first meter. The problem requires us to find the spring constant. The restoring force equals the negative of the spring constant times the displacement. However, we don't have the restoring force. We have the weight. Fortunately, the weight is just the same magnitude as the restoring force, just in the opposite direction. So if we are using the weight, we will just negate the other side of the equation and we will get weight equals kx. Dividing both sides by x, we will get this equation. The spring constant equals the weight over the displacement. Then, we just plug in the weight, which is 6.0 newtons. Then, to get our displacement, we will subtract the initial length from the final length, 5.0 times 10 to the negative first, minus 3.0 times 10 to the negative first meters. Dividing the two, we will get 30 newtons per meter. However, we have to make sure that it is clear that the 0 in 30 is significant. So, we can write our answer as 3.0 times 10 newtons per meter, showing that we have two significant figures. You're now ready for the experiment. Let us have Jericho since it's experiment time.
Experiment time. So in this experiment time, we want to show the relationship between the spring constant and changing the so that we will use a formula which is the Hooke's law wherein K is equal to force over delta X or change in length. In this experiment, the materials will be needed are two rubber bands, which is better if the other one is used and the other one is unused. Next is 500 grams of water, a meter stick or ruler, and also the apparatus which has a hook wherein we can hold the water for the rubber bands. As for the data sheet, we can see here that there are three triangles, so we get the average of this result for the spring constant. To start the experiment, you need a ruler, two rubber bands, and also a bottle that is a plastic so that it will hold the water inside. Okay? The mass of the water is 500 grams. And then the apparatus. Measuring the change in length of the rubber band number 1. For the second rubber band, we will use again the 500 grams of water to place in our apparatus. So let's see if it will be greater than the rubber band number 1 or it will be shorter than the rubber band number 1. For the results, we can see here in the rubber band number 1 or the unused rubber band, we can see here that the initial length of this rubber band is 6.5 cm, which is equivalent to 0.065 meters. And for the final length, or the wherein we place the 500 grams of water in the rubber band, you can see here that there's a 29.4 centimeter, or equivalent to 0.294 meters. So here in the problem, we are finding the Springs constant, which is equal to weight over delta x, or change in length. So W is equal to mass times gravity, which is equal to 0.5 kilograms times 9.8 meter per second squared. And for the denominator, which is the change in length, so final length minus initial length, so 0.294 meters minus 0.065 meters. So we can get the answer of 21.4 meters. As for the rubber band number 2, or the used rubber band, we can see here that I got a initial length of 7.8 centimeters, or equivalent to 0.078 meters. And as for the final length, I got the 31.3 centimeters, which is equivalent to 313 meters. And also we are finding here the Springs constant, which is equal to weight over delta x. So after equating the numbers, we can get for the rubber band number 1, we can get the Springs constant, which is 21.4 meters. And as for the used rubber band, which is the rubber band number 2, we can get the spring constant of 20.85 meters. So therefore, we can conclude that the greater amount of mass and lesser amount of change in length, the higher will be the Springs constant, which is, we are finding the proportion of the Springs constant and the change in length. So I noticed that when we lower the change in length, we can get the Springs constant to a higher value. So that's it. Thank you for listening.
Thank you for that, Jericho. That concludes our demonstration about Hooke's law. You might be asking yourself, why are we using rubber bands if Hooke's law is about springs? Well, because in this experiment we are stretching the rubber band, and it is perfectly fine to demonstrate the Hooke's law when you are stretching a rubber band because it acts similarly to a spring. However, if we are talking about compression, then it is not the same as compressing a rubber band because it doesn't have the same resistive properties. This experiment demonstrates that the spring constant is a quantity that measures the ability of an object to resist elastic deformation. The second rubber band, the used one, has a lower spring constant because it is less able to resist being stretched. The same amount of force has stretched it much further than the other one, the unused rubber band. That concludes this discussion. Thank you for watching. Jericho and I hope that you learned something and you had fun.